for this one here, it's already a single fraction, but if you can factor, which I can take out a common factor of a out of the top, and the bottom is a difference of squares, sometimes if you can factor, you can simplify further. Now I factored this, and the only way we can simplify is if factors are identical, and none of them currently are identical. They're close. I have a minus b and b minus a, which is close but not identical. However, you can factor out a -1. If I take a -1 out of this, the a would become positive and the b would become negative. So we can rewrite this take out that -1, I'll actually write a -1. And now these two are identical and they would simplify. So with the negative, you have a choice. You could put that negative out in front, which is what their answer has, the -1 in front. You could put that negative in the top. Or you could have left that negative on the bottom, either factored out or distributed. But the important thing in this one is to notice that if two factors are the same, but like so close to being the same, but one's a minus b and the other's b minus a, then you can factor out that negative to get the end. And what we're going to notice what happens a ton in this unit is this example. When you have fractions inside of fractions, okay? And I'm going to give, there's lots of ways you can work with this. But I'll give you some steps of what to do if you have fractions inside of fractions. First, this whole thing is a big fraction, right? And we have something in the numerator of that big fraction and something in the denominator of that big fraction. And what we want to do first is get a single fraction in both the big numerator and the big denominator. So what does that mean for us? Well, in ours, I need to add the two fractions that are in the top together to get a single fraction. If I want to add fractions, I need a common denominator. So between b and c, here I'd have to multiply by b and b. And here I'd have to multiply by c and c. And my top fraction is going to get a common denominator of bc, and I'll have ab plus c all over bc. In my denominator, right now I have b over 1 plus c over a. Again, I'm adding fractions. To add fractions, I need a common denominator. So I'm going to multiply this by a and this by a. I would get a common denominator of a. And now I have a single fraction in my numerator of my big fraction and a single fraction in the denominator of my big fraction. And you'll notice me like draw this line extra long, sometimes extra thick, so we can really see we have a fraction divided by a fraction. And then, of course, if you have a fraction divided by a fraction, then you can multiply by the reciprocal. So we would have AB plus C over BC multiplied by the reciprocal A over AB plus C. Sometimes when I have fractions, I add brackets when things are added or subtracted, because things that are added or subtracted in a fraction are considered one term. And the only way you can simplify that is if you have the identical term below. Sometimes you're going to be tempted to be like, ooh, I really want to just cancel out these b's. Not allowed, because this is grouped together. However, we could cancel out all of this. And that simplifies to A over BC. This is a huge idea in this unit. But instead of using variables, A, B, C's, and D's, we're going to use trig functions. Sine, cosine, secant, cotangent, tangent. And do a whole bunch of fraction work with trig functions. And this is something that's called identities. So in our notes, there we go. If you turn the page, the top of page 606, you can highlight this definition. What is a trig identity? It is an equation using trig functions that is always, always true. You already know from chapter 6, from your 3 big ideas, 2 of your big ideas from chapter 6 are identities. One of them, sine squared theta plus cos squared theta, no matter what theta is always equal to 1. That's a big idea. That is a trig identity because it's always true and it doesn't matter what the angle is. Another big identity that we had from chapter 6, tan theta is always sine theta over cos theta. And these are on your formula sheets, and I promise to get your formula sheets to you, and I have them ready to go. One more you need. It is a lot of formulas. Super. If you look on the formula sheet, from chapter 6, it has the S equals theta R right at the top. And then it has our first big idea, sine squared plus cos squared theta equals 1. Those are 2 formulas from chapter 6. Then everything else in the first column will be learned in the next couple of sections of chapter 7. There's a lot of formulas for chapter 7. And then you have to have them memorized for AP Calculus for next year. Okay. So, our definitions, our reciprocal functions, are also considered identities. Because by definition, cosecant theta is 1 over sine theta. And you can see where fractions come into play, because we already have a fraction there. Anytime you have a cosecant theta, you're allowed to change it to 1 over sine theta. Similarly, if you have a sine theta and you would like to, you could change it to a 1 over cosecant theta. Secant theta is 1 over cos theta, so cos theta is 1 over secant theta, and cotangent theta is 1 over tan theta. That also means that tangent of theta is 1 over cotangent. But we also have our big idea that tan was sine theta over cos theta, and we'll also have then, since cotangent is the reciprocal of tangent, cotangent theta will be cos theta over sine theta. And so to start off, these are the tools we're allowed to use. We're allowed to use any of the reciprocal identities and any of our big ideas, tan or cotangent or sine squared plus cos squared theta equals 1. and we're going to prove new identities. And so the next section of this course is proving identities. And I got a handout for you that we're going to start and do some together. I am one short in this row. Did I send an extra to any room? Or did I just count one short? Oh, I have one extra here because I stole. That makes sense. So what we're going to do is we're going to learn how to do a proof. And I also have, because you need to use loose leaf for this, so I've got extra loose leaf. If you have your own notebook that you like to use for work, then you can take a piece of loose leaf. And we're going to start with question number 5. And the first thing you do is rewrite the question. So it says prove, and we have cos of t, secant of t equals 1. Yeah, I started on the corners, so pass them to the inside once you're done. And then pass it off with newspaper. And then I'll take the extras in the end. Everybody got paper that needed? Okay. So we have some formalities for proofs. Okay? When you're proving something, the number one mistake in a proof is using the proof to prove it. You can't do that. So the first thing we do on a proof, we rewrite it, and where the equal sign is, we draw a straight line, and that tells us you're not allowed to move things from one side of the equation to the other. Because you're allowed to do that if the equation is true, and our job is to prove that it's true. So we can't assume that it's true to prove that it's true. So we draw a straight line, and we're only allowed to work on each side separately. Nothing can go over that line ever. So for example, can you see that if I divided both sides by cos theta, it sure would look like you've proven it, because secant theta is 1 over cos theta, but that is not allowed. All you're allowed to do is change things. So for example, I can change secant t. By definition, it's 1 over cos of t. That would be allowed because I stay working on the left-hand side, right? Because this is just one of our definitions right here. Secant theta is 1 over cos of theta. I'm allowed to use any of these definitions. And so here I have a secant t. I change it to 1 over cos of theta. This is an s, this is an s, this is a t.
Did you just say that c
Secant t is 1 over cos of t.
yeah. Okay.
And this is a fraction, right? So now I'm multiplying fractions. Can you see that this could simplify? Because you're dividing, they're the same thing. And we would get 1. This is our goal in a proof, to make the left side and the right side exactly the same. So the final formality for a proof is once you have them the same, you write a little statement saying you notice they're the same. Does anyone know what 3 dots like this? It's short for a word.
Therefore.
No, there's 3 dots. Do you know what it stands for? I'm kidding. You're right. It stands for therefore. Therefore, the left side equals the right side. It's kind of funny because you draw 3 dots. You liked that, didn't you? So therefore, the left side equals the right side. You've proven it. Now, at the end of mathematical proofs, this is often written. You like watch fancy math movies with proofs. At the end of a proof, you often have QED. It's short for Latin, which I probably can't pronounce it right, but it's like quod erat demonstratum, which loosely translated to English means what has been asked for has been demonstrated or has been shown. So I like to end it with that, and then I have my own little touch that I add on to a proof. I add a little box. I did this, I don't know, in all my proofs in university, and I still do it. You can, if you like to put a smiley face at the end of yours, there's something satisfying when you finish your proof. So that's makes me happy at the end. Okay? But all you would have to do is left side equals right side. But if you want to get fancy math stuff, you could add that QED to the end. All right, let's do another one. Number 5 was fairly easy. Let's try number 9. I like number 9 because number 9 is a good place to introduce to you a main strategy. Cos y, cosecant y equals cotangent y. So again, you rewrite the question and then draw a line where the equal sign is. Now the strategy I want to point out is based on an observation of all of these that we have so far. No matter which of the 6 trig functions you start with, you can change all of them to either sine and or cosine. So for example, if you have sine, you don't have to change it. It's already sine. And same thing with cosine. But if I go to cosecant, I could change it to 1 over sine. If I had a secant, I could change it to 1 over cos theta. If I have a cotangent, I have the choice to change cotangent to 1 over tangent, but I also could change it to cos theta over sine theta. And same thing with tan theta, you can change it to sine theta over cos theta. If you change everything to sine and cosine, your chances of the two sides matching up are a lot better than if you keep it with all 6 different ones. So we're going to see what that looks like in this question. I'm not going to change the cos, but I see the cosecant, and I decide to change the cosecant to 1 over sine. I see the cotangent, I could change that to 1 over tan, but I'm going to change it to cos over sine. Then, if you can do your fraction rules to get a single fraction on both sides, this would be over 1. How do I multiply fractions? Multiply the tops, multiply the bottoms, and they're the same. So, just changing it to sine and cosine and using your fraction rules to get a single fraction on both sides, I will tell you about 90% of proofs can be done this way. So we've got it done. So we've got left side equals right side. And we're all done. Well, let's do number 12. And this is where fractions inside of fractions starts coming up in these proofs. So we want to prove that secant theta over cosecant theta equals tan of theta. Oh, just wanted to point out, like, if you don't like y and you wanted to write theta again, you have to be careful. If you just decide you want to change it to theta and change your variable, that'll automatically come up as an E3 error. Because they'll look and say, there was no thetas in this question, and you changed the question to thetas. If you want to change the question to thetas, you actually have to state, I want to let y equal theta, or theta equal y. Then you're allowed to change. But if you don't state that, you're not allowed to just change your variables. Actually happened on an exam once. They had a question, and it was not an easy question. It was like a quadratic equation, secant squared x plus 3 secant x plus 1 equals 0. And then they said, solve for theta. There was no thetas in the question. So they gave every student who did that question that year 100% on that question. It was like the hardest question that had said solve for x. Super hard question. Called it a quadratic formula. Crazy hard. But they had a typo, and it made the question not solvable.
I wonder if anyone did like let x equal theta.
Maybe, and actually solved it, but they were nervous, right?
I feel like if you do that, you should get bonus points.
So here I'm going to do the same strategy, and the other thing, the reason I gave you paper, is identities need space. If you like to cram things into a little, like you're trying to save paper, you're going to end up having to redo them over and over again. You won't save paper in the end. Make sure you use space. And one of the things I do for spacing is like my next line, I'm going to change secant to 1 over cos. Big line for my main fraction over 1 over sine. I left some space in here, because when you have fractions inside of fractions, and you will have some questions that have fractions inside of fractions with fractions beside them and fractions everywhere, it can get very busy, and you need to keep your ideas organized. So I left a little bit of space there. Same thing on this side. I'm going to change my tangent to sine theta over cos theta. My right-hand side is a single fraction. My left-hand side has a fraction inside of a fraction. There's a single fraction on the top, single fraction on the bottom, so next I could multiply by the reciprocal. And multiply the tops, multiply the bottoms. And they're the same. The left side equals right side. Oh, yes. What? You like that pen? Okay. So on this paper, you can do up to 24. Once you get to 29, you will run into strategies we haven't learned yet. So we have to wait. But you can do up to 24. We'll now turn to example 1 in our textbook. And we're going to talk about the difference between the word verify and the word prove. When a question says verify for a certain angle, that means you have to plug that angle in, and you're still going to do left side and right side and see if they're the same. And after all of that work, you will show that the identity is true for that one angle. Proving is much more powerful. Once you've completed a proof, you've shown that it works for every single angle. Like, the proof means I no longer have to verify anything. I proved it. So you'll find I don't assign a lot of verifying, because it's much more powerful to prove something. But I will show you the work. If you have a verify question, you set it up the same way with the left side and the right side and a line, but you plug in the angle. All right, let's start with the cos. That's on your pi plane. Cos of 30 degrees, 1/2 or root 3 over 2? Root 3 over 2. Does it make sense then that secant would be 2 over root 3? Now that you have numbers, you still need the left side to equal the right side. So probably what I would do here, I might distribute this fraction. Let's see that you would get, 2 over root 3, and then when this fraction hits this fraction, can you see the top would be 2 root 3, and the bottom would be 2 root 3? Are you okay if I just make that 1? Are they the same? Yes. So they'll accept that you know that 5 plus 2 is the same as 2 plus 5. Like adding is the same even if the order is different. So I can go left side equals right side. And I've proven it.
What does the box mean?
It's just, I had a textbook in university that had a little QED and then they put a little box at the end. Some magazine articles, I don't know if you've ever seen a magazine now that everything's on the internet, but magazines used to get them and they'd be so full of ads that you'd start an article on one page and there'd be ads on the next page and ads on, and then be like, oh, it continued here and then wrote a little bit. And when they finish the article, sometimes they put a little symbol to say, oh, you don't have to keep flipping through ads to find the rest of it. It's done. The article is over. There's Maclean's used to use Canadian maple leaf with an M inside of it when they finished an article. So when I finish a proof, I put a little square.
At the end of that, you said we proved it, and you just said when you finished.
Sorry.
We just verified it.
We just verified it. That was the, yeah. And like I said, we're gonna do more proofs than verifications. Now we're gonna actually prove it. So to actually prove it, I'm going to use that main strategy. If you ever get stuck on a proof and come to me and say, Mr. Jarrett, I'm stuck, and I say, well, have you done the main strategy of first changing things to sine and cosine and getting a single fraction on both sides? If you haven't done that, I'll be like, well, you can't ask yet because you haven't tried the main strategy. It normally works. Okay? So I'm going to do that here, and then we're going to talk about other possible strategies we could use. So if I use the main strategy, I change secant to 1 over cos theta on both sides. Then I would say, okay, I want to get a single fraction. Can you see that this 1 plus cos theta could be all over 1? And if I multiplied fractions, I would multiply the tops and multiply the bottoms. And on the right-hand side, I'm adding fractions. I need a common denominator. I'm going to make a tiny mistake, and we'll see if we can find the tiny mistake at the end. So I want to get a common denominator, so I'm going to need to multiply this by cos over cos, and that's going to give me common denominator of cos theta, and I have cos theta plus 1 Are these the same? Yes. Therefore, left side equals right side. And we're all done. But I would have got an E3 error on this question. What did I do that was sloppy?
On the big one, it actually one over one, so it's like the top.
One, this one here, is 1 over 1. Okay, I wouldn't lose, if I didn't write 1 over 1,
No, but like when you multiply.
I did imagine multiplying the top and the bottom to get cos theta over cos theta and add this to 1. There's still another E error here. What do you think?
Multiply by cos instead of cos theta?
I forgot the theta. It's super important. Cos by itself means nothing. Right? If I take one letter out of your name, and now you have a new name, it could be completely different. R-E, without the L. Take out the S. Total confusion in your family. Joe. Right? So it's super important to have the theta on there. Even if they will, on your exam, you're doing work, you're doing a proof, and in the bottom corner, you want to remind yourself that tan is sine over cos. You do this in the tiny bottom corner of your paper. Looks like it has nothing to do with the work you're doing. You still get an E3 error for that little bit in the bottom corner. If you do that, rip your corner off and throw it away, burn it. No, don't burn it, but not get in trouble for starting fires during exams.
Put it in your pocket and then burn it when you get home.
So this would be an E3 error there as well. Some of you are going to collect lots of E3 errors. And hopefully, after collecting a few of them, you'd be like, okay, I've got enough. I don't need any more E3s.
Always put that theta over x or whatever.
Mm-hmm.
Actually, a question. For
Yes.
me putting it into the putting something into the corner, would it matter what symbol you put next to it, even if the question itself that you're answering uses a different? Like if the question was using cos x, but you use cos theta.
They'd probably be fine with that, although it is also an E3 error if in your work you change variables. So, but just off to the side as its own variable with theta or x probably would be fine.
If there was cos x, and then you said let x be theta, but you never used the theta.
That'd be fine. As long as you say let, you can let a whole bunch of stuff at the beginning and then not use any of it.
Unless they use both of the variables in the question.
So you want to use the variables that were in the question.
Well, yeah, but if they put two variables in the question, you could just say, let this variable be equal to this other variable, while they're both used in the question.
Usually there's not two variables in the question.
Well, yeah, but.
Can I put let me pass this exam? Let me pass.
I wouldn't just let you pass. That would be a nice thing to try.
Just at the start of the exam, let
The variable is false.
So for the second one, we're just going to do the proof. Okay? We're going to do the proof, and we're going to do the proof in two different ways, because even though the main strategy of change to sine theta and cos theta is very good, it's not always the best strategy for a proof. That's one of the things that makes proofs really fun, is you can do it and solve it one way, and then be like, I wonder if I could do this a different way, and then see if you could solve it a different way. So I'm going to show you the proof for this one in two different ways. First, I'm going to go with the standard, change everything to sine and cosine, and get a single fraction on both sides strategy. So for tangent, I'm going to change that to sine theta over cos theta. And for cotangent, I'm gonna change to cos theta over sine theta, minus 1, and I've got and here we have something very similar to what we had at the start of today's class, where you have fractions inside of fractions. Okay. On the left-hand side, do we have a single fraction? No, this is 1 over 1. I want to get a common denominator, so I'm going to multiply by cos theta and cos theta. To get a common denominator of cos theta. And I end up with cos theta minus sine theta. On this side, I have fractions over fractions. So first, I want a single fraction in both my numerator and my denominator. Can you see right now that you do not have a single fraction in your numerator? I'm going to need a common denominator to subtract these. So, do you notice the little bit of space that I left in between? Just so that, because with so many fractions, it's easier for your brain to lose something or get things mixed up. Notice also that I made the main fraction line longer and the other fraction lines a little bit shorter to really see a fraction on the top and a fraction on the bottom. Right? Because sometimes it could be confusing. Is this, what is that? Is that 3 divided by 4/5? Or is that 3/4 divided by 5? Does it make a difference? Yeah, that's different. Those are going to be different numbers. One says 3/4 divided by 5. One says 3 divided by 4/5. If I had done this,
Well, that's a 3/4.
now you can't tell if it's a 4 or a 9. I know it's wrong. But
Okay,
it looks a little bit more like 3 divided by 4.
okay, now it's a third divided by
Right,
5.
so how we write things, it's very easy for things to get a little bit confused. But now I have a fraction divided by a fraction, so I can multiply by the reciprocal. Now with fractions, you can multiply the tops and multiply the bottoms, but before you multiply, add brackets to, that's one thing, so I would not be able to cancel out my sine thetas because I'm adding or subtracting there, right? But before you multiply things out, you can simplify. Did you know that trick with fractions? Like if I got you to do 113 over 17 times by, well, I'll put on here maybe 97, yeah, and 17 here. If you had to multiply this out mental math, the numbers are huge. But if you know that you can simplify these 17s, you just get 113 over 97. That's a lot easier. Okay? The same thing happens in our fractions here. Don't distribute this yet. Look, if you have identical factors and you're multiplying, you can simplify. Then, what am I left with? I'm left with cos theta minus sine theta in my numerator, all over cos theta. Is it the same?
Yeah.
Then we better take out a fancy pen. I once had a student ask, how do I know when to make the QED fancy looking and when to make it just plain? It doesn't matter. You can just tweak it. It's just the fun part at the end. Okay. So this is proof one. This is using the main strategy. Get good at the main strategy. It develops your fraction rules. Change everything to sine and cosine, and then you have to get a single fraction on both sides, which means adding and subtracting, you need common denominators. If you have fractions inside of fractions, we add or subtract to get a single fraction in our numerator, single fraction in our denominator, and then multiply by the reciprocal.
Can I go to the bathroom? But also, I have a question about the last one.
Well, the last one, I can pull it up.
When you did like the
With that,
cos theta plus the cos theta, like plus the 1, why wouldn't it be 2 cos theta on the bottom?
If you're adding fractions, does your denominator change?
Oh,
Right.
the thing.
Because they're the same.
Okay, that makes
Okay, so sometimes, but this is a good point, because sometimes we have a question about a rule because we're dealing with weird stuff, right? You weren't adding fractions in grade 6 with cos theta on the bottom. This is weird for your brain, it's not used to it. So your brain likes to sometimes like make up new rules because you're dealing with weird stuff, so why don't I make up some weird rules as well, which causes problems. So if you're wondering, should the bottom change? Well, think about regular fractions. No, here you would just get 7/3, right? Don't change the bottom there, get a common denominator and then add them, so you won't change it here either.
has the red light on your thing been flashing this entire time?
Oh, it's just starting to flash. That means the battery is just starting to go.
Okay.
So, I don't know if it's still working. Probably the best would be to charge it
You just have
and switch to the backup. Which is, oh, it's on.
Well, it's just straight.
There we go. So this looks like this would be better for karaoke. Okay. Now, this is the main strategy. Some other strategies, so I'm going to prove this one with another strategy. Another strategy that would come into play in this one is, I notice the left side has tangent, the right side has cotangent. And I know there's a connection between cotangent and tangent. The whole first strategy of changing to sine and cosine is so you're dealing with the same thing. Chances are the proof will be the same on both sides. Why not change this one to only tangent or to only cotangent? And one of them will be nicer than the other. If I change to only tangent, you see on the right-hand side, changing the cotangent to 1 over tangent, I'll have fractions inside of fractions, and it will seem relatively about the same amount of work as the previous strategy. But if I change my tangent to 1 over cotangent, and I still use the strategy of, let's get a single fraction on both sides, right? This is 1 over 1. I would have to multiply by cotangent over cotangent, because that's how you add and subtract fractions, and I would get a common denominator of cotangent, and the top would be cotangent theta minus 1. And we're done. Wasn't that quick? Like this, I'd be like, wow. And I spend a whole bunch of time.
each of the periods in your QED are your little boxes.
I know, I like that part. That was way quicker. That's a nicer proof. So you can play around with proofs after you solve the proof one way. You can be like, is there a better way? Is there a quicker way? Can I use some other math skills that I have? As long as I'm not breaking math rules, you're allowed to do it. You can get quite creative. As soon as you start making up stuff, you start losing marks. And number one mistake that students make with proofs is they, first of all, just make a regular mistake, and things aren't working. So they're like, well, I just ignore, like, if I just write the other side, maybe they won't notice I made any mistakes. This is not a good idea, because you will lose a mark for your first mistake, and then they'll be like, okay, they've done some, oh no, they did another mistake at the end. And all of your proofs on your exam and on your quizzes and on your tests, they will all be provable. I'm not out there to trick you. The exam is not out there to trick you. They're not going to put one on there that is like, no, this can't happen. They'll always work, okay? The other thing, oh yeah, here, I'll show you with this proof here. I'll do this one in a different way.
There you go, trace that perfectly.
As close as I'm gonna make it. There we go. So let's say I start by distributing, because that's a mathematical thing you're allowed to do. So I would get secant theta plus secant theta cos theta. Agree?
Mm-hmm.
Okay? You are allowed to do this. How can I make secant theta cos theta equal to 1? Well, on your definition is this, right? Can you see in that definition that if you multiplied both sides by cos theta, you would get secant theta cos theta?
Mm-hmm.
And on this side, you'd be left with 1.
Mm-hmm.
So you were allowed to change secant theta cos theta to 1 because on one of the things that you're allowed to use, you can get from here to here with one mental math. I call it one mental math manipulation. You only have to do one mental math thing, you're able to do it. The biggest one you're going to use over and over again is you're going to see sine squared theta, and you're going to change it to 1 minus cos squared theta. And you're just doing a single manipulation of sine squared theta plus cos squared theta equals 1. You just move the cos squared theta over. That's allowed. But anytime you start to do more than one mental math manipulation, you're going to lose marks for not showing your work. I had a final exam. Let's just pretend this was the proof. Let's pretend this one, part B, this was a proof on a final exam. I had a student once write, ladies and gentlemen, okay, it is obvious that cos theta equals 1 plus cos theta over 1 plus secant theta. So their proof looked like this.
Oh no.
Left side equals right side. QED. I just did all that math in my head. Well, that would take, there's no way that you can just do one mental math thing to change cos theta to this. So they obviously didn't get any marks for that, but it was very entertaining. They said it is obvious that cos theta equals 1 plus cos theta over 1 plus secant theta. No work needs to be shown. Left side equals right side. QED.
And then you got the big fat zero. Yeah.
But look, it made me so happy I'm still telling the story.
I'm sure that student will be happy that this is their legacy.
That's their legacy. I mentioned on a YouTube video. Alright, so for question 1, your practice questions are 3, 5, 6. And 7, 5, 5.